The next section is called CO2 Effects on Climate. And this section doesn't necessarily think about how carbon dioxide affects climate, but really for how long the CO2 that's in the atmosphere is going to remain in the atmosphere, and how long we can think of the carbon dioxide effects on climate to remain. Much of the increased concentration of fossil fuel CO2 will remain in the atmosphere for hundreds to thousands of years. Now we know the mean residence time of CO2, we know the rate that it's being taken out by different sinks, and when we put that all together, even if we were to stop all emissions, much of the carbon dioxide, that additional carbon dioxide that's in the atmosphere, is going to remain in the atmosphere in one form or another for hundreds to thousands of years. Part of this really has to do with the idea of Caesar's breadth principle. Not necessarily that when you take a look at the Earth, that a given molecule is going to travel all around the Earth, but also that the mean residence time is relatively long, and the CO2 that is taken up eventually is going to get released, and long-term sinks are relatively slow to accumulate. When we do the calculations, if all of the anthropogenic emissions ceased today, so we stopped all fossil fuel burning, we're looking at somewhere on the order of half of the carbon dioxide that had been emitted would be absorbed within 30 years. We expect that 30% of that carbon dioxide would remain in the atmosphere for centuries. And 20% would remain in the atmosphere for thousands of years. So we would see an elevation of CO2 concentrations in 1,000 years that still would be elevated relative to pre-industrial. Now it's important to know that there are 4 reasons why CO2 disappears so slowly. First, the efficiency of the land and ocean sinks is weakening. So we know that the ability of oceans to absorb CO2 and the ability of vegetation to absorb CO2 is declining over time. That as CO2 concentrations in the oceans build up, for example, there's less of an ability of those oceans to absorb CO2. In addition, the oceans are warming, for example, and there's reduced solubility of CO2 at higher temperatures. So for a number of reasons, that efficiency of how well the land and the ocean can absorb CO2 is declining. And so we can't expect those sinks to be maintained at the current rate. Secondly, the deep ocean, which is the major long-term sink for CO2, equilibrates very slowly with the surface ocean in the atmosphere. So if you have your ocean, and we divide it up into 2 parts with the surface and the deep, that we know that although these surface waters could become saturated or have elevated CO2 concentrations, the rate of movement of particles through that biological pump, but also the movement of in thermohaline circulation of shallow water to deep is a relatively slow process. And as such, it's that long-term sink is going to take a while to soak up additional CO2. There's also stabilizing feedbacks that minimize changes in ecosystem carbon pools. So for example, as productivity goes up in ecosystems, you might be more likely to have fire, because fire in part is dependent on fuel load. And so the more biomass that we have in systems, the more likely you are that you're going to have release of CO2. And so there's a whole set of stabilizing feedbacks that we're not going to cover in too much detail, nor does the book do that, that really minimize how much carbon can get absorbed in these more active pools. Lastly, it's the weathering of silicate rocks that is a really large sink for CO2 on geologic timescales, but it's a very slow process. And so even though we have a lot of silicate rock that can be weathered and absorb a lot of CO2 in the process, it's a slow process, and we can't expect that to be used to reduce atmospheric CO2 concentrations anytime soon. And there's this idea that there's 2 sides to buffering, that having silicate rocks to weather is a good thing, but it's relatively slow as far as absorbing CO2 concentrations. Now, as far as thinking about changes in the climate and the effects of CO2, that the authors have a short point that's important to reemphasize here, that oceans temporarily absorb heat. So a lot of the increase in temperature has gone, a lot of that heat, additional heat, has gone into heating oceans. And there's been expansion of ocean water, for example, as a result of this. But oceans have been getting warmer all throughout the world. And even if we start to lower CO2 concentrations, for example, that heat is going to be emitted and it's going to be re-radiated over time. So this is a sink for temperatures, it buffers temperatures, but also as the atmosphere cools, if we were to ever bring down fossil fuel emissions and CO2 concentrations started to go, you have this large reservoir of warmth, of heat, for example, and that's going to get re-radiated and it's going to buffer temperatures also long term.